step. Replace all the f of things with the appropriate function. F of 28 plus h is equal to what? 6 times 28 plus h plus 15 minus, in parentheses, 6x plus 15. And all of that now divided by h again. Just one step to the next, just following the formula and replacing things in the way that they should be replaced. Okay?
How come you're at 28 on your second half of that disappeared?
Because I got lazy. All right. Now what? Well, now multiply everything out as we need to. Okay? Multiply the stuff out to the top as we need to, and simplify it to see if there's a way of getting rid of that h in the denominator. Can't divide by things really small that well. Get rid of that tendency and see what happens. Well, let's see. I'm going to get, and I'm going to leave this as 6 times 28 because I don't want to have to multiply it out. This is plus 6h plus 15 minus, oh, there's another 6 times 28. That's good. Go away. And then plus a 15 there. All of that now is still divided by h. Okay. Simple distributive law stuff. Let's see. Then what cancels out? What goes away? Okay, so the 6 times 28 goes away. The 15s go away. I have a plus 15 and a minus plus 15, so those go away. And in this case, what I'm left with is something very simple to calculate. At this step now, my h's will cancel out. And what I'm left with is 6. So what this tells me is that for this particular function, this 6x plus 15, as I look at what happens to this function near x equals 28, I'm finding that at that particular instant, this graph is changing by about 6 units. This function is changing at a rate of 6 units per whatever I want to measure it against. Now, does that come as a surprise to you? Is that a surprise? Why not? Because look at this graph that we were looking at. The graph we're looking at is the equation of a line. What's the slope of that line? What does the slope of a line tell you? It tells you how fast that graph is changing. That's what the slope of this line is telling us. So it shouldn't come as a surprise that the slope of this graph and the instantaneous rate of change at x equals 28 are exactly the same. In fact, in this problem, I could change this x to any value I wanted to. And this rate of change is going to be the same. Okay? This function is changing at a rate of 6 units per whatever, no matter where I look. Alright. So that is our rate of change stuff. Okay. That then concludes 2.1, and we can now start in on 2.2. Section 2.2 is all about working with limits. For some of you, this may be second nature. For some of you, this may be new. All right? The importance of limits in calculus is essential, because as we can sort of see from some of these examples we've been working with, each one of these problems that we've done today has in some way dealt with this concept of a limit. Now, what is a limit? Well, a limit is just sort of this notion of looking at what happens to, I guess in calculus terms, we're looking at what happens to a function as we get very close to specific values. Okay? For example, if we look at the following function, f of x equals x squared minus 1 over x minus 1. I want to know what happens to f of x near x equals 1. What happens to this function as we get closer and closer to that x equals 1? Well, the first thing I might try when presented with a problem like this is to say, well, let's plug x equals 1 in and see what happens. What happens if I try to plug x equals 1 in? I get a 0 in the denominator, but I also get a 0 in the top. In this particular function, 0 divided by 0, well, oh my god, what happens there? I mean, how do you come to terms with 0 over 0? What we really need to do here is we need to try to figure out, okay, is there a different way that I can approach this problem? Okay? I want to take this problem right here and I want to say, okay, what happens near x equals 1? One thing I can do is I can try to, again, make my little table of values. I'll look at x over here, and I'll look at f of x over here. And all I'm going to do is just plug in values very, very close to 0, very, very close to 1. For example, if I look at x equals 1.1, f of x in that case is 2.1. If I look at 1.01, f of x is 2.01. As I continue to look at values, I don't want to just look on the positive side of 1. I don't want to look at just what happens on values just slightly bigger. I also want to look and see what happens to values slightly smaller. In this case, at 0.99, I get 1.99. And as I continue to get smaller and smaller values, closer to the x equals 1 value, what do I notice about the values of f of x? They never actually get to 2, right? But if you look at what's happening to them, they are getting closer and closer and closer to x equals 2. Now, if we were to graph this function, would the graph support these numerical conclusions that we're coming to? Well, the graph of this function, if you were to put it into your calculator, will give you out something that looks like this. And that should be the line, not something curvy properties. There's what the graph of this function right here looks like. Does our graph seem to support the conclusion that our numbers here are telling us? Sure seems that way, right? Now, you'll look at this and you'll say, there's a big hole in our graph. You screwed up, you put a big hole in it. I didn't put a hole in here just because I screwed up. The hole's here because I can't ever plug x equals 1 into this function, can I? This function does not have a value at x equals 1. There's no value. Even though the function gets closer and closer to x equals, or to y equals 2 here, the function itself does not have a numerical value. Now, it's great that this numerical evidence and this graph both support the idea of the value of this function being closer and closer to 2 as x gets closer and closer to 1. But why is that? Can you think of a way of justifying this picture and these numbers without referring to those numbers or those pictures? Why do we get this graph from this function? Is there something about this function we can do to sort of see why this function looks like a line, except at x equals 1? Okay. If we look at this function a little bit more, f of x equals the x squared minus 1 over x minus 1. For those of you that have seen factors like this before, the top here factors nicely into x plus 1 times x minus 1. The denominator, again, our x minus 1. when we factor it down in this form, it's pretty easy to see now that we can cancel out the x minus 1s. We can cancel those out. And what we get is we get that our function, f of x, is really just the function x plus 1 in disguise. However, because our original function looked like this, we have to keep that same domain down here, and we have to still say x can't equal positive 1. Okay? That restriction from up here follows us all the way through. Even though we canceled the x minus 1s out, the original functions had that x minus 1 at the bottom. That has to stay with us the whole problem. Okay? All right, so a little example of what we're doing with limits. Let's talk a little bit about a more formal definition of what a limit is. So we say f of x has a limit L at x equals a if f of x is as close as we need it to, as close to L near x equals a as we want. This is a somewhat informal definition. There is a much more technical definition that we could apply to this, but for our purposes, what we want to know is all encompassed in this one little phrase here. Okay? This sort of unmathematical part of this definition is the as close as we want to. Mathematicians are very anal about being precise. This is one of those times where I'll get away from it because the formal definition does not lend itself to anything that are right. Okay? So in terms of a picture, you can imagine that we have some function that does some crazy stuff. When we say that this function has a limit of L at x equals a, so let's just put a little point A here. Okay. What we're saying is that if we focus around that point x equals a, if we just focus right around here, if we focus just in and around this point A, does our graph seem to sort of get pinned down to a specific value within that area right there? If you notice, inside this little red set of parentheses here, our function is sort of pinned in between. Direction you pin things. Our function value is sort of pinned in between those two red dotted lines. When I say f of x gets as close to L near x equals a as we want, what that means is that if I shrink this sort of interval down further and further, these two red dotted lines, I can make them get smaller and smaller. And provided this function has a limit, that L value is going to be pinned in between two red dotted lines that are essentially zero width apart. That's what it means to say that a function, f of x, has a limit as x approaches a. It means I can find two dotted lines to sort of pin my graph in between, and I can shrink those lines down as I get closer and closer to a, to basically having zero width, which gives us a limit value like this. Okay? In terms of notation, the notation we use for something like this is the following. Limit's always abbreviated by lim. Underneath